going to finish off the chapter on matrices. So there's something we've seen once or twice. So first is the object that if you take a 2 by 2 matrix and get out the right down diagonal minus left down diagonal. And the other one we've seen is the, I'm going to write this a bit funny here, but say you got the I, J, K, say, let's call this UX, UY, UZ, VX, VY, VZ, and you get out this thing with the bars where you do the right down diagonals as well. So this thing is a function called the determinant of a matrix. And what it does is, now in the case of what we saw in chapter 1 on the right there, that actually is a vector, but in general it should be a number. Okay, so it associates to a vector. So actually, in fact, I should really rub this one out. It's possibly confusing us. I'll do maybe, can I do a very simple determinant, say 1, 2, I'll put in loads of zeros now, 0, 1, 0, 0, 1, 2. Will this even work? So the right down diagonals give me 0, 0, they're all coming out 0, aren't they? I think one of them doesn't. I think you get 2, 1, 2 here. So I'm just thinking out loud, yeah, I think I get out the number -4. Okay, so anyway, you put a matrix in, you get a number out, and this is called the determinant of the matrix. So we're going to calculate 2 by 2s and 3 by 3s. They're basically just calculated as right down diagonal minus left down diagonal. But we need to explain what they are, and to explain what they are, we'll use matrices. Okay, now I'm going to have to do something a little bit dodgy. So yeah, maybe I can get away with it here. So we're going to take an original area. So maybe actually what I'm going to do isn't going to be dodgy. So this is an original area. And then we're going to see, yeah, no, I'm going to have to cheat, sorry. Yeah. So take an area A. So what I'm saying is not 100% right, but should work. So that's the first region, and then the second region says something like this. Okay, third region says something like this, and the fourth, well, I don't want to put it there. Second region something like this, and fourth region something like this. So this isn't going to be perfect, but it'll give us an idea. So this is going to have an area of A. Okay, so what the determinant is basically is a scale factor, and I think that's what I've written up there. So what you can do is, if you can imagine, so if you look at the region A, there's infinitely many points in it. Now really, if I did this properly with rectangles and stuff, you only have to do it with 4 points. But just imagine that you've got all these infinitely many points, including the boundary, and you give them to a matrix M1, and it sends all these points to all these points. So everything along the boundary gets sent to the boundary, and anything in the interior gets sent to the interior. So say, for example, you take this point here, this might get sent to that point there. Okay, so the original region gets sent to this other region here. Now what the area of this new region, bar the few kind of cheats that I'm talking about, the area of this will be the determinant of matrix 1 times the original area. So it's like a scale factor. Okay, now if you take maybe better to that in blue. So the area of this is the determinant of M1, or A times the determinant of A1. Okay, now imagine a second matrix which sends points here onto the line. So maybe this point up here gets sent over here, So I'm saying this, sorry, this point here maybe gets sent here, maybe this point here gets sent here, this point here gets sent here, etc. So what you have is a two-dimensional shape going to a one-dimensional shape. Okay, so the area of this will be the original area times the determinant of M2. And then the last one is all the points get sent to a single point. That's multiplying by M3. And so the area of this little dot will be the original area times the determinant of M3. Okay, so if a 2 by 2 matrix M1 is applied to a region of area, then the area of the image will be this. Now, here you can see that the determinant of M1 must be less than 1. And in fact, we're going to be a little bit more careful. The absolute value of the determinant M1 is going to be less than 1 because the area has gotten smaller. Okay, now what about this one? Now if you look at what's the area of a line, well, you can talk about the length, but the width is 0, so the area of a line is just 0. So the determinant of M2 here is equal to 0. And similar story, the determinant of the area of a single point is 0, so the determinant of M3 is equal to 0. And you can show that you can't send back with a matrix. Now you can do it with other things, but a matrix, you can't send back from dimension. So let's look at the dimensions of these bits. This thing is dimension 2. This is dimension 2 as well. This is dimension 1. And the point is dimension 0. And you can show that a matrix can't send something from, now you can go from dimension 1 to dimension 2, that's no problem, we can do that, but you can't send, so what I'm trying to say is if you go from a dimension 1 to dimension 2, all you end up with is a dimension 1 space. So the matrix is kind of reduced dimension, sorry, they can't increase dimension, essentially. Well, there's a bit more going on there in the background, but if you can imagine in the line, there's an infinite amount of points, but in the region of dimension 2, it's doubly infinite, and you can't send back. So basically what you have is M2 is not invertible, M3 is not invertible, but M1 is invertible. So we're going to have written down quite soon, a matrix is invertible only if the determinant is non-zero. So the only one of these that has an inverse is going to be M1, excuse me. The other ones, it will not be possible. Okay, so determinant is a scale factor, but it also helps you figure out if a matrix is invertible or not. This will all be written down. So M1 is invertible, M2 and M3 are not invertible, and another word for not invertible is singular. So you can now what you can do here is so what I've taken is some vectors. So this is, say, the 0 vector. This actually is I, isn't it? This is actually j, and this is I plus j. So look, this is 0 vector, I, j, kind of seen as points more as vectors realistically. And what's the area of this? The area of this is 1. And so if you take a matrix A, B, C, D, now what you can show is that, okay, so 0 is sent to 0, j is sent to BD, I is sent to AC, and I plus j is sent to A plus B, C plus D. So we're saying that the determinant is the scale factor. So the area of this should be 1 times the determinant of, now let's just call this yoke M for matrix, 1 by the determinant of M. And you can show with a bit of work that the area of that kind of parallelogram is AD minus BC. Right down diagonal minus left down diagonal. And you can generalize that, but it gets very difficult. Okay, so what do we got? So that AB, a square matrix with column vectors, the determinant of A is the volume of the parallelepiped generated by the column vectors. Now you don't really need that. You just need to know that how to calculate 2 by 2 determinants, 3 by 3 determinants, know that they're scale factors, and we'll write down something in a second. If the determinant is 0, the matrix is not invertible. If the determinant is non-zero, it is invertible. So the determinant of a 2 by 2, easy enough, you've seen this before. Right down diagonal minus left down diagonal. no bother. So you got this theorem, says that a matrix is invertible if and only if. Now the if and only if means it goes both ways. So if it's invertible, then the determinant is non-zero. And if the determinant is non-zero, then it's invertible. And it also includes more theorems. If A is not invertible, the determinant is not non-zero, so it is zero. And if the determinant is not non-zero, in other words, if the determinant is zero, then the matrix is not invertible. So this is captured in this table. So basically what it's saying is that these are the same thing. So we can say, maybe we can write this down another way. Not invertible is equivalent to the determinant of the matrix being zero. Okay, now that's probably one of the harder things in this module for students if they're going into an exam, but of course your assessment is open book, so you got a bit of a chance there. Now the proof basically says if the determinant is zero, it's impossible, because you can't go from, say, dimension 4 to dimension 3 and come back to dimension 3 to a fully dimension 4 space. That's not possible. If the determinant is non-zero, then what you have is there is this kind of abstract formula that basically works. Okay. Now this thing, I don't think we need this. Not in this module. Okay. Another one of this, a way of saying this is that the inverse exists exactly when the inverse of the determinant exists. So what the hell does that mean? Well, something to that, see, so let's write this down. So this yoke is a number. And this number to the power of -1 means 1 over this number. And this is fine as long as it's not equal to 0. If the determinant is equal to 0, then 1 over the determinant, 1 over 0, this thing does not exist. Yeah, so look, there's different ways of looking at it, but this is one way of looking at it. The inverse exists when the inverse of the determinant as a number exists. Yeah, okay, all right. So let's do some examples. Find the value of t for which the determinant of this is equal to 0. So this, look at this thing, this could be rephrased. For what value of t is this matrix not invertible? Because not invertible is the same as the determinant being 0. Let's see how we're doing for space here. Okay. What's a bit weird is I actually have it done out here. Is that the same question? That's a bit dumb. Yeah, I'm going to, that's very dumb. So I'm going to scrap this and just go through the worked example just to save us a little bit of time. So here we go. So the determinant, remember, is the right down diagonal minus left down diagonal. So 1 by -6. That's there. Take away the left down diagonal, which is t plus 3 by 3t. And you need to be careful here in terms of the multiplying out. So I think we could take an extra line here and just be very, very careful. So the 1 by the -6 is -6. I'm going to keep the minus. And then t by 3t is 3t squared. And then plus 3 by 3t is 9t. And then multiplying the -1, I get this thing. So what we want to do is we want to solve this equal to 0. Now, depending on, like, if you're going to do maths again next year, I presume you did factorizing quadratics last semester. If you're going into level 7, you want to be able to factorize these. So what I mean by that is you want to be able to go kind of from here to here. In this module, that's not really my concern. This is called the quadratic equation, by the way. To be honest, I'm just not going to have these equations on the assessment, so I'm not going to worry about it. It's something you should have seen last semester. There's an option as well to use a -b formula. Okay, Yeah, so I'm going to leave it at that. So basically, okay, what's the question here? Find, calculate the determinant, no problem, solve it equals 0. If I ask you this, the equation will be simpler. Right, so there's a American scheme question. What are we looking at here? Okay, now we're going to have, oh no, these are exercises as well. Now, next question, how to calculate the determinant of a 3 by 3. Luckily, you've already done this. We've done this in the vectors. Now, we could talk about calculating 4 by 4 determinants, but it's a bit of a pain. So we're just going to fix to 3 by 3. So we've done it before, so we'll just review it. So say the matrix you want to calculate the determinant of, let's say it's 2, 1, 0, 6, 10, 5, minus 2, minus 1, 3. So just like before, so that means those bars mean I want the determinant of this matrix, the scale factor. So just like before, you write the first two columns again. Now there's no ijk's here. 2, 6, minus 2, 1, 10, minus 1. And then you do the right down diagonals minus the left down diagonals. So we'll do the right down diagonals, 2 by 10 by 3, 1 by 5 by minus 2, 0 by 6 by minus 1. So the 2 by 10 is 20 by 3 is 60. 1 by 5 is 5 by minus 2 is minus 10. And the last one is 0. And now we're going to take away the left down diagonals, 1 by 6 by 3, 2 by 5 by minus 1, 0 by 10 by minus 10. So the first one there was 1 by 6 by 3 is 18. Next one, 5 by 2 is 10 by minus 1 is minus 10. And the last one is 0 by anything is 0. So this is 60 minus 10, which is 50. Take away, looks like 8. 42. Okay, so you've actually seen that before, so no kind of bother. So let's see a better example. So this will be one without a quadratic equation. So the question is, for what value of k does this not have an inverse? So you'll have to go away and have a think how you kind of learn this. So for me, it doesn't have an inverse if the scale factor is 0. It's as simple as that for me. There's a kind of, it's written there in kind of a bit more length. We have the theorem that a matrix is invertible if and only if the determinant is non-zero. Therefore, the matrix is not invertible if and only if the determinant is 0. And we've also got this, the inverse exists if and only if the inverse of the determinant exists. So the inverse of a number exists as long as it's non-zero. So if the inverse of the matrix does not exist, the inverse of the determinant does not exist. That means the determinant is 0. There might be a bit of confusion here. This bar and this, they mean the same thing. They're just, it's like dy dx and y dash of x. They mean the same thing. So what we're going to do here is we need to calculate the determinant and set it equal to 0. So the determinant of a is equal to, now there's no ijk's, and this k is nothing to do with the k hat. It's just an unknown. Minus 1k4, 2k4, 4, 3, minus 2. So the question is to find this equal to 0. So let's calculate this thing by doing the first two columns again. And we do right down diagonal minus left down diagonal. So minus 1 by k by minus 2, 2 by 3 by 4, 4 by k by 4. So the minus 1 by k gives us minus k, by minus 2 is 2k. The next one is 2 by 3 is 6 by 4. What's 6 by 4? I'm drawing a blank. It's 24, isn't it? 6 by 4. Jeez. Yeah, of course. Sorry, I'm gone a bit thick. Well, not thick, but anyway, right, 4 by k by 4 is 16k. And then the left down diagonals. So I get 2 by k by minus 2, minus 1 by 3 by 4, 4 by k by 4. So if anything's too fast, pause it. 2 by k is 2k by minus 2 is minus 4k. Minus 1 by 3 is minus 3 by 4 is minus 12. And the last one, 4 by k by 4 is 16k. And we're doing right down diagonals minus left down diagonals. Right down diagonals minus left down diagonals. And what do I get for the determinant? So I get, I could be a bit smart and do 16k minus 16k. That's probably a good idea. And do 2k minus 4k is 6k. And I have 24 minus 12, which is 24 plus 12, which is 36. And now we're interested in this equal to 0. If this is equal to 0, the matrix has a determinant of 0 and it's not invertible. So this is kind of more the level of equation I probably want to assess you on. Yeah. So I want to solve this for k. I'm going to take 36 away from both sides. 6k is equal to minus 36. And I want k on its own. It's multiplied by 6. So I need to do the opposite of multiplying by 6, which is dividing by 6. And if I divide both sides by 6, I get k is equal to minus 36. Bingo bango. Job's a good one. Okay, so that's everything I wanted to say about determinants. So calculating a 3 by 3, no problem. Calculating the determinant of a 2 by 2 is even easier. It's just right down diagonals minus left down diagonals. Easy enough. And what I really want is that you understand that a determinant is a scale factor. And that kind of tells you if the determinant is 0, you're going from a full dimension to a smaller dimension and you can't come back, so you can't invert. If you go from dimension 2 to dimension 2 or dimension 3 to dimension 3, you can invert. Okay. Oh, I should have pressed the other button first. Sorry now. Wasted a few seconds there. Oh, Jesus.